So the first definition that we're going to look at is the Arrhenius definition, and you were introduced to this in Chem 1A. Under this definition, an acid is a substance that produces hydrogen ions in an aqueous solution. So many of these acids are actually molecular compounds, but when you dissolve them in water, they form ions. The example here is HCl, which in its pure form is a gas, hydrogen chloride. When you dissolve it in water, it forms the ions hydrogen ion and chloride ion. A base, under this definition, is a substance that produces hydroxide ions in aqueous solution. So these hydrogen ions. Let's think about what is a hydrogen ion? A hydrogen atom has how many protons? One. And how many electrons? One. When you make it into a positive ion, it loses its one electron, and what's left? A proton. A hydrogen ion is just a proton. That's like crazy tiny, right? I think of hydrogen ions as being like newborn babies. They don't go out on their own, right? They only go out when they're being held or pushed in a stroller or something by someone who's larger, right? So these hydrogen ions, these protons, are not very stable. They're very reactive, and they will bond to water to form hydronium ions. So this is the formula for the hydronium ion. And there are other species that exist, but we just need to know, oh yeah, those could exist. We're done with that. So we often use H plus and H3O plus interchangeably, but we do that with the understanding that when we write the hydrogen ion by itself in an aqueous solution, we know that it's not actually by itself. It's being held by a water molecule. And this is how that happens. Here's a Lewis diagram for a water molecule. Water has two of these lone pairs on the oxygen. Hydrogen is, got no electrons. And so hydrogen can come over here, and oxygen is generous and will share two electrons with it to form a coordinate covalent bond. And now this is going to be more stable than just that proton by itself. Sodium hydroxide is a base because you dissolve it in water and it produces hydroxide ions. Unlike the acids, sodium hydroxide is an ionic compound. In its solid form, it has ions. When you put it into water, it just dissociates. The ions separate from each other. So here we have sodium hydroxide dissolving in water. We get separated sodium and hydroxide ions. Producing hydroxide ions tells us it's a base, an Arrhenius base. When these hydrogen ions combine with hydroxide ions, they combine to form a water molecule. So this is how acids and bases neutralize each other. The hydrogen ions from the acids, hydroxide ions from the base, come together and make water. It's not acidic or basic anymore. Any questions yet?
So if you combine the right stuff, you can just get water.
Yeah, you combine the right stuff, you just get water. In fact, those acid-base titrations we did in Chem 1A, provided you didn't like crazy overshoot the endpoint, you could probably drink that slightly pink water and it really wouldn't hurt you. It wouldn't taste very good, but it's just salty water, like sodium citrate. I don't recommend doing that though. Just don't want to get in trouble. So here's a second definition, the Bronsted-Lowry definition. All of these definitions are named after scientists. So this one applies to a wider range of compounds. Here we're talking about the transfer of hydrogen ions or protons. So an acid is a proton donor, and a base is a proton acceptor. So HCl is an acid because it donates this proton to a water molecule, forming the hydronium ion. And this more accurately tells us what actually happens to that hydrogen ion. It's not that the hydrogen ion and the chloride ion separate, and then we've got this tiny, lonely hydrogen ion just floating. That's not actually what happens. The hydrogen ion is actually just handed off from the HCl to the water. This definition also works with bases like ammonia. Look at the formula for ammonia, NH3. Doesn't look like it's a base, doesn't have any hydroxide ions in it. But it still produces hydroxide ions when dissolved in water, and it does that by accepting a proton from the water. So here's NH3. The water molecule can give a proton to it, and then we get ammonium ion and hydroxide ion. And what we understand from this definition is that acids and bases always occur together because there's a proton donor and a proton acceptor. You can't have one without the other. Some substances can act as acids or bases, and they are said to be amphoteric. So that's a funny word. Amphoteric. Ampho like amphibian, right? So if we look at an acid-base reaction in reverse, this is just the reverse of what happens when ammonia is dissolved in water. We see that we have ammonium ion and hydroxide ion. And the way they get from here to the products is that the ammonium ion donates a hydrogen, donates a proton to hydroxide. Hydroxide accepts the proton and becomes water. So what we see is that this substance, which was formed by the base, now becomes an acid itself. And so the difference between an acid and a base is one proton, a hydrogen ion. We call these pairs conjugate acid-base pairs because you can't have an acid without a base. So the conjugate pair, well, let's go back to the top of the slide. A conjugate acid is what you get after the base accepts its proton. Because now it has a proton, it can turn around and donate that to something else. So now it's an acid. It's the conjugate that related to the original base.
Why is H2O labeled as an acid?
Because it's an acid.
I thought it was neutral.
It's neutral and it's a base. It's amphoteric.
Oh.
So a conjugate base is the acid after it has acted like an acid. Acids donate protons. After the acid has donated a proton, now it's a conjugate base. And so one of the things that you do need to be able to do is identify conjugate acid-base pairs. And they are different from each other by a proton, a hydrogen ion. So here we have ammonia. If we add a hydrogen ion to this, we get NH4+. So here, this is the base. It accepts the proton, becoming NH4+. This is the conjugate acid. It can donate the hydrogen off to something else and become the original base again. So a lot of just handing off protons. Here's water, which can act as an acid. It can remove a hydrogen ion. We can remove a hydrogen ion from it. That's it acting as a base, and then That rewinding. Here's water. Water can act as an acid. It will donate a hydrogen ion to something else, to the base out there. And what we have left is the hydroxide ion. This is the conjugate base. The conjugate base can accept a hydrogen ion from something, and then we get back the original acid again. Any questions? In each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. I don't think it's important to have a clear distinction between what an Arrhenius acid is and what a Bronsted-Lowry acid is. I think it's much more important to be able to identify an acid. So the fact that it's giving this particular definition, don't worry about that. Identify the acid, the base, the conjugate acid, and the conjugate base. So looking at this first chemical reaction here, what we want to do is we want to look at where does the hydrogen ion go? Well, here water had 2 hydrogens, and over here it only has 1. So that means that the water lost a hydrogen ion, right? Donated. And it would have to donate it to the other thing. So the water is donating a hydrogen ion. Is that an acid or a base? That's an acid. So this is the acid. And then this guy over here must be the base. So that's our base. Now on the other side, this is the one that's very much like that base. The only difference is this has an extra hydrogen ion. So this is the conjugate acid. So that's the conjugate acid. And hydroxide is the conjugate base of water. Questions? If we look at these 2 reactants and we're thinking, well, all acids start with H. Well, yeah, water starts with H, but we don't generally think of it as an acid. It doesn't have acid in its name. And we can't just say, well, bases are always metal hydroxides. Because here, this is a base, and it doesn't have a metal in it or hydroxide. Okay, let's look at this one. HNO3 plus H2O, making H3O plus NO3 minus. Who donated the hydrogen ion? The HNO3. So the hydrogen ion went from the HNO3 to the water molecule. So that makes HNO3 the acid, and water here is the base. Oh wait, up there it was an acid. Yes, it's very versatile. Can do both. So then over here, what's this guy? This is going to be the conjugate acid of that one, because it has the extra hydrogen ion. And this then must be the conjugate base. So a hydrogen ion, a proton, is being transferred from one thing to another. The thing that currently has the hydrogen ion is the acid. Okay, which of these pairs is not a conjugate acid-base pair? What we're looking for is the difference in the formula to be just H+. One has it, one doesn't. What about these 2? Is this a conjugate acid-base pair? Yeah, it is. They both have the CH3,3N, and this one has that H+. So this is the acid, and that's the base. How about these guys, H2SO4 and H2SO3? No. This is a different number of oxygens. These are not a conjugate acid-base pair. How about HNO2 and NO2 minus? Yeah. Okay? So I think of, that hydrogen ion, that proton as being a little tiny baby, and the acid has the baby and passes it off to the babysitter, the base, right? Well, then the babysitter, the base, becomes the acid because now they can hand the baby off to someone else. So let's just pass the baby. I don't know.
Sounds like a good way to lose the baby.
You would not do that in these days.